Welcome to a lesson with Dr. Powell. Let's suppose that we have a function, and we'll use x this time. And suppose we think about this function as being odometer readings. And suppose we want to know what the precise speedometer reading would be right at a particular value. Suppose maybe right at the value 2. Okay, so what is the speedometer reading right at 2? So at x, we want to know basically what the IROC of f of x is at x equals 2. How would we do that? Well, we just need small intervals that are close to 2 that contain 2. Now, 2 just has to be inside of it. It can be at either end. On the other examples, we had our thing at the right endpoint. We could even use the left endpoint, 2. Then we could go a little bit out and make that arbitrary, like maybe we go h out. So we have a little interval starting at 2 and going, starting at 2 and going h away this way to 2 plus h. That means that h is the run. How do we compute the rise? Well, we compute the rise simply by finding the difference of y values from this point to this point. So the y value here is f of 2 plus h, and the y value here is f of 2. Just rise over run. Rise, f of 2 plus h minus f of 2, run, all over h. This expression right here, as h gets very, very small, should go right to the instantaneous rate of change that we desire. Now, right away, we cannot plug in h is equal to 0 into this because it's not defined. So instead of plugging h in, we use a little notation, meaning that we see what this quantity or expression will get close to as h gets close to 0. We can't actually plug in 0, but we can see what this expression gets close to by maybe algebraically reducing this equation when h isn't 0. And then if we reduce to something that we can actually plug 0 into, we plug it into, and it is actually what this gets close to. So that's called taking a limit. So let's proceed and see if we can do this. So we just plug in 2 plus h into that function. 2 plus h, quantity squared, plus 2 plus h. Then we subtract what happens when we plug in 2. We get 6, 4 plus 2 is 6. And all that is over h, which is the run. Now let's simplify. Let's multiply that out. 4 plus 4h plus h squared plus 2 plus h minus 6 all over h. See this 4 and 2 and 6, they cancel. Now this h then can divide into each one of the remaining guys right here. Maybe we should rewrite this as, so let's rewrite this as 5h plus h squared, and then we can divide the h into each part. Notice what we get. We get 5 plus h. Oh my goodness. So, well, we can do that division here, assuming that h isn't 0, we can cancel. So away from 0, when h isn't 0, this is what the average rate of change is. But as h gets really, really small, we may as well just plug in h being 0 to see what the expression gets close to. That's called taking a limit. So plugging in h is 0 here, we end up getting 5. So the instantaneous rate of change is 5 right at the x value of 2. Thanks for watching.